Okay, we were discussing about this wavelets in the previous class. We have seen that how this wavelet system is analogous to your Fourier series. Okay, so in the Fourier analysis, what we have done that a function which is periodic, it can be expressed as a linear combination of complex exponentials. And in the wavelet analysis, a function can be expressed again as a linear combination of wavelets. Okay, so you can express a function in the form of a linear combination of some wavelet functions multiplied with some coefficients ajk. Okay, so it maps a one-dimensional function into a series of two-dimensional parameters, whereas this maps one-dimensional function into a series of one-dimensional coefficients. Okay, so this we have termed that, okay, if you find the for any particular function f of t which is given to you, which may be non-stationary or transient in nature, so if you can express this function in terms of a series like this, where wt is a wavelet and wjk, these are basically obtained from this mother wavelet using the scales and translation. So if you can decompose a function like this, so these coefficients, expansion coefficients, we call these as discrete wavelet transform of this function ft. Okay, and then we have seen that how wavelet is more effective as compared to the Fourier analysis, because in the Fourier analysis the basis functions, they are fixed. We have sine and cosine functions, so it is well suited for stationary signals or periodic signals. Okay, but if the signal is non-stationary or there are transients in the phenomena, then wavelet is a more effective tool. Okay, because the wavelets, they themselves have sharp corners, okay, or they are not in fact smooth functions. Okay, so the transient phenomena in the signals, it can be represented in the wavelets domain by the wavelet transform dwt coefficients. Okay, again we have seen that in the Fourier series that these basis functions, they must be orthogonal to each other, and similarly in the wavelet transform, if the wavelet functions, they are orthogonal to each other, then of course you can find the dwt coefficients using the inner product between the function and this basis functions. Okay, so today we will discuss about multi-resolution analysis or multi-resolution formulation of wavelet systems. Okay, see, many times you will see in the theory of wavelets that apart from the wavelet function, we define one more function which is called as scaling function, represented by phi t. Okay, and then we have one more, of course, wavelet function psi t. So you will see in this formulation that a function f of t, that can be decomposed in terms of not only wavelets. We decompose a function using a scaling function and a wavelet function. Okay, or in fact we first start from a scaling function and the wavelet function is obtained, or it is designed from the scaling function. Okay, so what we do in the multi-resolution analysis, suppose we have a scaling function phi t, and we will take this, we will take some examples from a wavelet family which is called as Haar wavelet. This is a very basic wavelet system. In fact, the first wavelet system that was designed by this Haar, which is termed as Haar wavelet. So we'll take, in order to explain this concept of multi-resolution analysis, we will take some examples from this wavelet system, Haar wavelets. Okay. So what we do, before you start with this MRA, we define some basic uh, terms like space, signal space, S, or vector space. Okay. So vector space, if you decompose a function, in terms of some basis functions, okay, so we have seen that if this decomposition is unique, then we call these functions, decomposition functions, as basis functions. Okay, and the set of all the functions f of t which can be decomposed in this form, so that set is basically called as signal space or vector space. Okay, and we say, okay, these functions, these wavelet or the basis functions, they span this space as vector spaces. Okay, and then we define the inner product between two functions that you already know. If you have two functions f of t and g of t, so their inner product is defined as integration of ft star into gt dt. Okay, the star is for conjugates, complex conjugates. And then this inner product is also used to define the norm of a vector, norm of a function f, or we call it as L2 norm, which is given by square root of inner product of f with f. Okay, so it is basically integration, or in fact mode of this. Okay, so square root of the mode of the inner product of a function with itself that defines the norm or the length of this function. Okay, so this you can see, if you see, if I'm not variable the vector spaces, like in this, what we do, suppose you say you have a vector maybe in one dimensional, so if you have vector a and you have vector b, not in continuous time, in the discrete domain. Okay, so how we define the inner product of the two vectors a b? It is nothing but summation of ai star into bi over I. Okay, so a conjugate into bi plus a1 conjugate into b1 and so on. So if it is not a complex vector, it's a real vector, it is simply the product of their corresponding coefficients, which is called a basically dot product. Okay, in vector terminology. And when you define the norm or the length of a vector, we generally take, so if a is a vector and if this vector has suppose two elements a1 and a2, so these elements in a geometrical space, they represent the coordinates of a point in two dimensions. So this is a1 and this is a2. Similarly, if it has three elements a1, a2 and a3, these are the coordinates of the point in three-dimensional space. Okay, if it is in generally n-dimensional vector, so these are the n coordinates. And if you find the length of the vector, this is what is called as norm. Okay, denoted by this, we call it as L2 norm, which you basic, or we call it as equality distance in fact also. So this is nothing but what? This is under root of a1 square plus under root of a2 square. So this is simply under root of a1 square plus a2 square. This is called as L2 norm, which defines the length of this vector. Okay, so similarly when you have functional spaces, we define, so it is inner product basically of a vector itself. Okay, so if you find inner product of this vector itself, a and a in the product, it will be a1 into a1, it will become a1 square plus a2 square, and then you take square root of this. This is how you define the norm, and similarly we have done here. Okay, so you have multiplied the function with itself. Okay, and then of course in product, that means you have to integrate it and take its square root. You will get the norm of the vector. Okay. So this is what is a functional space or vector space. So functions are basically represented by vectors as vectors. Okay, and if a function is decomposed in the form of a set of basis functions, so that set of all these functions forms this vector space. Okay, and we say that these basis functions, they span this space. Okay. Okay, so we will discuss what is MRA and multi-resolution analysis. So we start from some scaling function. Phi t, and we define a space, vector space V naught, as the set of all those functions which are generated by using psi of t minus k, where k is an integer. Okay, so V naught is the space of the functions which can be generated from this translation. So you have psi t minus 1, psi t minus 2, psi t minus 3. Okay, and then you combine them with some coefficients and you generate some functions. So the set of all functions that can be generated using these translations, that is suppose V naught. Okay, so we write it as V naught as the span of phi t minus k over k. Okay, and we also write a bar here. It is basically called as closure. Okay, closure means that not only those functions which can be represented by phi t minus k, but limits of those approximations also. Okay, that is the meaning of this bar. It's called as closure. Okay, so V naught is the span of phi t minus k. So span means the set of all those functions which can be represented by phi t minus k, or you can say if ft belongs to this span V naught, then this function can be written as this form, phi t minus k, isn't it? Okay, and then we can increase the space or the subspace by changing the scale in the scaling function. So if you generate a function, scaling function using 2 raised to power j t minus k, 2 raised to power j phi j k t. Okay, now this we have already done in the wavelets. Okay, why we use this scaling factor of 2j in order to maintain the norm of the scaling function. So if you scale this scaling function and you translate it, so you can generate a space, suppose Vj. So Vj is the span of phi jkt over k. Okay, and of course since in phi 2 raised to power jt minus k, you are scaling the wavelet and then you are translating it. Okay, it means those functions which belongs to this space Vj, they can be represented by this form ak phi of jkt. Okay, where j and k, these can be any integer values. Okay, now if you have suppose, it means v naught is space for this phi t minus k, then we define is space v1, which will be basically for when j is 1, that is for phi of 2t minus k. Okay, phi 2t minus k, it means you have scaled this scaling function, you have compressed it by a factor of half, and then we translate it, you have to translate in half steps. Okay, it means the space of v1 will also contain the space that is spanned by v naught. Okay, is using v1, now you can generate a space which is basically a superset of v naught, right? What it means actually, suppose you take a simple example of let us suppose I take a hard scaling function, otherwise you may not understand it. Hard scaling function is basically defined as a unit width and unit height pulse. This is hard scaling function, phi t, rectangular pulse. Okay, 0 to 1, its height is 1. Now what we are saying that, let us suppose that v naught is the span of this function phi t minus k. Okay, it means all the functions which can be generated by the translates of this scaling function, that set basically gives you this function, this space v naught. Okay, and you can see if you shift, if this is my scaling function, hard scaling function phi t, then I can take it as phi t minus 1. If you take phi t minus 1, it will be shifted by 1 to the right. Then you take phi t minus 2, shifted by 1 to the right, and so on. Okay, so if you multiply with some, then you can multiply, this is phi t, this is phi t minus 1, phi t minus 2, and so on. So if you multiply these phi t minus 1, phi t minus 2 with some coefficients ak, so you can generate some functions which are piecewise linear, isn't it? So you may multiply, suppose phi t with 1, it will remain 1. Then you may multiply phi of t minus 1, suppose 1 by 2, its magnitude will become half. Okay, then again you may multiply phi of t minus 2 with 2, it will go here. Okay, then you have maybe phi of t minus 2, if you multiply the negative value, it will go here, like this. Okay, so you can generate functions like this, which are piecewise linear functions. Okay, so the set of all these functions is the space v naught. Now what we are saying that you can increase the space, okay, of the scaling functions by changing the scale of the scaling function. It means from phi, now we are generating phi of 2 to the power jt minus k, these kind of functions. So if you have suppose phi of and j is 1, scale is 1, you have 2t minus k. Okay, so the span of this is, I am saying it is v1. Now when you have phi of 2t minus k, okay, it means you can now have phi 2t, you can have phi of 2t minus 1, you can have phi of 2t minus 2, and so on. So what will be phi of 2t? This is my phi t, so phi of 2t will be compressed by a factor of 2, so it will go from 0 to 1 by 2 only. Then phi of 2t minus 1, So phi of 2t minus 1 means what? Phi of 2t minus 1, how you generate it? So you start from phi t, then you scale it by factor of 2, you'll get phi of 2t, and then you shift it by half to the right, you will get 2 of t minus 1 by 2. This is how you get phi of 2t minus 1. Okay, it means you have phi of 2t, this function is phi of 2t, and then you translate it to the right by half. So you will have a function like this. This is phi of 2t minus 1. So compression by half, then shifting by half. Similarly, phi of 2t minus 2 means you have to compress first phi t by 2, and then you have to shift it by t minus 1. You will get phi of 2t minus 2. Okay, so this is the signal which is compressed by factor of 2. Then you have to shift it by 1. Or alternative, you can say that you have compressed it by half, then shifted by 1 by 2. You have to shift it again by 1 by 2. You will get like this. So it was from 1 by 2 to 1. It will now go from 1 to 3 by 2 and so on. Okay. Now in fact, in this space, phi 2t and phi 2t minus 1, they can be combined to generate this function phi t. If we simply add these two functions, phi 2t plus phi of 2t minus 1, we will get phi t for this case. Okay, so here phi t is nothing but phi 2t plus phi 2t minus 1. What it means is that since I can generate this function phi t from these two functions, phi 2t minus k, it means all the functions which can be generated from phi t, they can also be generated from phi 2t and phi 2t minus 1. Okay, so that is why we are saying that if v1 is the space of phi 2t minus k for j is equal to 1 scale, it means v1 or v0 is basically a subset of v1. So those functions which are in v0, they will obviously be a part of v1. Why? Because the basis function which we are using in this space v0, that can be generated from the basis functions which we are using in v1 space. Apart from that, there may be some other functions which can be generated from these two functions. Okay, so all those functions which can be generated from this, they will obviously be generated from these two, because by combining these two you get this. Okay, so any function which can be generated from this function, that can also be generated from these two functions. But apart from that, there may be some more functions which you can generate using these two sets only. Okay, and similarly, if you change the scale now, if you go to a scale of 2, so you have psi of to the power 2, it will become 4t minus k. So psi of 4t minus k means that now this scaling function is basically compressed by half, no sorry, by 1/4. You will get 0 to 1 by 4 1. This is psi of 4t. Then when you have psi of 4t minus 1, it means you have to shift it by 1 by 4. Then I have psi of t minus 4t minus 2, shift again by 1 by 2, shift again by 1 by 4, not 1 by 2, sorry. So this is phi of 4t, then phi of 4t minus 1, phi of 4t minus 2, phi of 4t minus 3. Okay, and if you say that okay, v3 is the space of all the functions which can be generated from phi 4t minus k, obviously v1 will be a subset of v2 also. So v0 is a subset of v1 and v1 will be a subset of v2. because if you combine these two functions, if you simply add these two functions, you can get this function, and if you add these two functions, you can generate this function. Okay, so the expansion functions of this space V1, they can be generated from the expansion functions of this space V2. It means whatever signals you can represent in V1, okay, they will of course will come in V2 space, and V2 space will have even more signals which can be represented, which may not be represented by this space. Okay, so as you go on increasing the scales, so this is a basically nested loop of these spaces. So here V naught is a subset of V1, it is a subset of V2, V2 will be a subset of V3 and so on. And similarly, if you decrease the scale, it will be a subset of V minus 1, V minus 2 and so on. Okay, so when j reaches to infinity, your V infinity, it becomes L square R. Okay, L square R means this is the space of all the square integrable functions. Okay, L square means all those functions for which you can find the integration of the square of the modulus. This is what is called as L square R space. Okay, all the functions that exist for which you can find the mod, the square and its integration, those fall in this space L square R. Okay, so as you increase the scale, it means you are basically reducing the width of the scaling function. It will become more narrow and more narrow and more narrow. So as you increase the scale, you are getting more and more resolution or more details information in the signals that can be captured at higher scales. Okay, so you can also denote this like this. So we have this space, this is suppose V0 and this is V1. So V0 is a subset of V1, then V2, so V1 is a subset of V2, and then V3 is a subset of V2. Okay, so this is V3, this is V2, this is V0, and this is your V1. Okay, so this is the space of V0. It means all the functions which can be represented by phi t minus k only. And then we have changed the scale from j is equal to 0 to 1. We have got another space V1, this space. So of course this V0 is basically now a part of this V1, or it is a subset of V1. So apart from this space, we have some other function else here left, this space, which can be represented by the scaling functions in this span of V1. Then we have V2, then we have V3. So V2 space, this is the entire space of V2. So of course V2, whatever functions can be represented or whatever functions they fall in this span V2, they will also be a part of V1, they will also be part of V2, but apart from that span, you will have another functions which can be represented, which are basically not available in this span of V1. Okay, so we are saying that that V0 is the span of phi t minus k. That means you are not basically scaling the function, you are taking just its dilations, you are shifting it just. And then V1 is the space that is spanned by phi of 2t minus k. So we have used scale 1. Okay, now since V1 is a subset of V naught. Okay, so what it means actually is that phi t itself, this function phi t, it can be generated from phi 2t minus k. Okay, so it means you can express this scaling function in terms of its own scale and translates. Okay, so you can write phi t as summation over n h of n under root 2 phi of 2t minus n. Okay, so this root 2 is again just to maintain the norm of the scaling function. Okay, we already discussed this. Like, see, when the scaling function, when you generate this psi of jkt, so you use 2 raised to the power j by 2 psi of 2 to the power j t minus k. So if you have scaled this t by 2 raised to the power j, you have to multiply the scaling factor, which is under root of 2 to the power j. Okay, so this you can write as 2 to the power j raised to the power 1 by 2, or square root of this. Okay, similarly in the continuous Wavelet transform, we have said that okay, we have psi of t minus tau by s. So you are scaling the time by a factor of 1 by s. So to maintain the norm, we have multiplied with 1 by under root s. Okay, similarly you're scaling it by a factor of 2. So to maintain the norm of the scaling function, you have to multiply with under root 2. Okay, so this equation says that you can express phi t in terms of phi 2t and its translates. Okay, because it is necessary that okay, if v1 is sorry, this should be v0, this is v1 here. So if v0 is a subset of v1, and since v naught or v0 space, it is generated from the functions phi t minus k, and v1 space, it is generated from the functions phi of 2t minus k. Okay, it means phi 2t minus k, this function, so this should be also available in this function v naught. Okay, so see, in the Haar system you can directly see this, how this equation is valid. We have written that phi t can be expressed in terms of phi 2t. Okay, so h of n square root of n phi 2t minus k of phi 2t minus n summation over n. So if you take the Haar function, Haar scaling function phi t, this is Haar function. Okay, and how can I express phi t in terms of phi 2t and phi 2t minus 1? If you compress it, you'll get phi 2t, which is 0 to 1 by 2, 1, and then phi 2t minus 1, it is shifted by 1 by 2. This is phi of 2t minus 1. So phi t, it can be generated from phi 2t plus phi of 2t minus 1 simply. If you add these two functions, you will get this function. Okay, it means if you solve this equation, what is the, it means your n in this case will go only from 0 to 1. So for some functions you may have n is equal to 0 to 2. It may also be required that n may vary from 0 to 3 and so on. But for this function, Haar scaling function, you have only two scaling functions phi 2t and phi 2t minus 1, and they can be used to express phi t. So what should be, it means I want two coefficients now, h0 when n is 1 and h1 when n is 1. So what will be h0 to satisfy this equation? Because we are multiplying with root 2, so h0 should be 1 by root 2 and h1 should also be 1 by root 2. Okay, so in this equation, if you put this as 1 by root 2 and 1 by root 2, so 1 by root 2 and root 2, they will get cancelled. Your phi t will become this. So this is basically, this is what is called as a scaling filter. Scaling filter coefficients. So for R transform, the scaling filter coefficients are 1 by root 2 and 1 by root 2. Okay. And this equation is a very important equation, which is called as multi-resolution equations, or we also call it as a refinement equation. And this equation is the basis towards this multi-resolution formulation. Okay, because of this equation only, because you can express phi t in terms of its own scales. It means if phi t, it spans a space v0, then phi 2t minus k, it spans a space v1, and in that case here v0 will be a subset of v1. Similarly, v1 will be a subset of v2 and so on. Okay, so it means you start from one function, one scaling function. Okay, and this function f of t, any function you can take, that can be decomposed in terms of phi t, then phi 2t minus k, then phi 4t minus k, 8t minus k, and so on. Okay, so as you increase the scale j1 2 3, so this pulse is going to become narrow and narrow. So for 1 it is 1 by 2, then if you take 2, it is 2 to the power j4, it will be by a factor of 4, then by factor of again 3, it is 1 by 8. Okay, it means the details, what you say, that as we change the scale, the higher scales, they capture the details in the signal, and the lower scales, they basically give you the coarse information. Okay, average information, what you say, but the higher scales, they provide you the detailed information. Okay, now later on, once you have defined a scaling function phi t, and we have seen that if the space v0 is the space of these functions phi t minus k, then phi 2t minus k, the space of this is v1, and of course v1 will contain all those signals which are basically in this space v0. Okay, similarly, if you go to higher scales, if you say phi of 4t minus k, and it has a space v2, so this will again contain all those signals which are in v1 or v0. Apart from this, it can also generate some other functions which may not be in v1 and v0. Okay, so like this, you can cover this entire space of L scalar functions, scalar integrable functions. Okay, and then we introduce another function which is called as a wavelet. What this wavelet does, basically, you have a nested space. Okay, so this is space of v0 and this is the space of v1. Okay, it means in this space of V1. Okay, these functions V0, they will be also available in space V0, but then there is a set of functions which are not available in V0 space, but they are available in V1. Okay, so we introduce a function which is called as wavelet, which is basically used to span the difference between the spaces that are spanned by these scaling functions. It means V1 space. Now this remaining space in the V1, it is spanned by a different function which is W0. Okay, so wavelet function at 0 scale. So V1 will be now union of these two spaces, and these two spaces, they are basically disjoint. Okay, because V0 is the space which is created or generated from the functions that is phi of t minus k only, and then V was the space which was generated by functions phi of 2t minus k, and this space also contains all the signals of this space. Now out of this, from this space V1, the space which is left uncovered by V0, that is basically covered by a wavelet function W0. So it spans the different space, and W0 and V0, they are disjoint basically. Or you will see that the scaling functions in V0 and W0, they are orthogonal to each other, or in fact orthonormal within the norm. Okay, and similarly now you can say that okay, this is the second space V2, which is spanned by these functions phi of 4t minus k. So V2, this function, the set of functions in V2, they are also in V1. But then this space which is left, that will be covered by another function at that scale, that will be W1. So wavelet at scale 1. Okay, now these two, this is the space of V1, and this is the space which is left, W1. Okay, so this is covered by the wavelet, not scaling functions. It means V2 can be taken as V1 and union of these two, V1 and W1. Okay, so V2 covers a more space. Some part of that is basically covered by V1, so the left part is covered by W1. Okay, it means V2 has many functions which can be represented in this space. So some functions, they can be represented by V1. Rest of the functions, they have to be represented by the wavelets. So these will be represented by scaling functions, the rest will be by wavelet functions. And since V1 is this, so you can write it as V0, W0 and W1 and so on. Okay, so if you take V infinity, which is L square space, so that can be taken as V0, W0, W1, so on. It means you have only one scaling function now. Okay, so rest of the space, that is all covered by the wavelet functions. So in general, we have used the scale 0 here for scaling function. Otherwise, you can start from any scale. Suppose V10. Okay, then next will be your W10, W11, and so on. Or you can even start from a lower scale, maybe V minus 5. Okay, then you will have W of minus 4, W of minus 3, and so on. So if the scale j in v goes to minus infinity, okay, in that case you will only left with the wavelets, no scaling functions. Okay, so in that case you can decompose the function in terms of wavelets only jkt, which is what we have discussed in the earlier when we have discussed discrete wavelet transform. Okay, now see, since w naught is basically now a subset of v1, okay, it lies in the space of v1, and v1 it is basically spanned by psi of 2t minus k, and w naught, it means there is no scaling, j is 0. So it means your wavelet function psi t, it should also be expressed in terms of phi 2t minus k. So this is another equation now. So psi t is equal to summation over n h 1n under root 2 phi of 2t minus k. This is again another refinement equation for the wavelets. Okay, one thing is that you have to express, or you can express phi t in terms of phi 2t, and then psi t, which is the wavelet function, this is also expressed in terms of phi t. So that is why we say that we first select this scaling function, and then the wavelet is obtained from the scaling function using this refinement equation. Okay, so for this, again for this Haar system, how you can do it is very simple. This is scaling function phi t, and if you see a Haar wavelet, how it looks like, a Haar wavelet is like this: 0, this is 1 by 2, 1, this is 1, and minus 1. This is a Haar wavelet. Okay, and if you see its average value, that is 0. So average value 0 means there must be some oscillations in the wavelet. Okay, so as to discriminate between different frequencies. So if you use this now refinement equation, that okay, I can express this psi t in terms of phi 2t. So I have taken a function here, some coefficients h1n, square root of 2 phi 2t minus k. So how you can write this function in terms of this function? You have to simply first compress it by a factor of 2. You will get phi 2t. Second function, this is 0 to 1 by 2. Then you have to take phi of 2t minus 1. It will become like this. So if you multiply this with minus 1, its amplitude will be reversed. It will become like this. So this function is phi of 2t minus 1. This is minus 1. So if you add phi 2t with minus of phi 2t minus, you can get psi t. It means what should be these coefficients? Your h10 should be equal to 1 by root 2, and h1 of 1, it should be equal to minus 1 by root 2. This is the solution of this equation for a Haar wavelet. Okay, so these are called as wavelet filter coefficients. Okay, so initially we have seen that we have scaling filter coefficient, which was h0 of 0 is equal to 1 by root 2, and h0 of 1 is also 1 by root 2. This is the solution for this equation. Okay, when you have written f phi t as summation over n h0n under root 2 phi of 2t minus k. So for this you get these coefficients, which is called as scaling filter coefficients, and for this we got this coefficient, which is called as wavelet filter coefficients. Okay, so it means now, so what we have concluded here is that in order to span this space of all square integrable functions, we start from a scaling function at scale 0, and let us suppose that the span or the set of all the functions which can be represented by that function, and it translates is V0. So rest of the space that is left, it is basically spanned by wavelets only. This is what is called as multi-resolution analysis. Okay. So as you increase the scales, it means you are getting the detailed information. So the coarse information is basically obtained from the scaling function. The detailed information that is obtained from the wavelet functions. Okay. So when you will see in this later on this filter banks, when you implement this DWT using filter banks, so you will see that the scaling filters and the wavelet filters, they are used for decomposition. Okay, and you will see that at the end you have left with, after the decomposition, you will be left with a scaling coefficient, and rest will be the wavelet coefficients. Okay, so using this you can decompose now any function f of t, not only in terms of the wavelet functions only, but in terms of scaling functions also. So you can write the DWT as summation of C of k phi of kt plus summation over d of jk psi j kt, where k from minus to plus infinity and j from 0 to infinity. Okay, so this is a new equation for discrete wavelet transform. So you have scaling function and the rest are all wavelets. So scaling function we have used at 0 scale. Okay, so there are just translates, only psi of kt, phi of kt is used. So phi kt means it may be phi kt is basically phi of t minus k. Okay, and then these dj in place of aj, now we have used dj, which basically are used to you can say represent the detailed information in the signal. Okay, so you change j is equal to 0, then you compress it by 2, then by when j is 3, compressed by 4, 8, then 16, 32, 64, and so on. Okay, and k is just used for again the translation. Okay, it means if you have some function, and you want to express this function in terms of the wavelets and the scaling functions, so you have to choose a scaling function. Let us suppose it is Haar scaling, and then you have wavelet function. So you have phi t, then you have psi t. Okay, so this psi t will be only shifted in time by k is equal to 1, 2, 3. So shifted by 1, you will go here. Shifted by 2, it will go here, and so on. So these multiplied, these functions will be now multiplied with some constants. So c0, c1, c2, and so on. So what is ck here? Okay, so c0 means it is multiplied with psi t. Sorry, this is phi t. Then c1 and k is 1, it is multiplied with phi of t minus 1, then phi of t to t minus 2. So the coarse information in the signal is basically captured by the scaling functions, and then rest informations will be by wavelets. So you have j is equal to 0, it means the same function without any scaling, then k is equal to 1, k is equal to 2. To shift it, you will get one set of coefficients djk. Then you compress it by factor of half. This becomes psi of when j is 1. Okay, when j is 2, it is compressed by a factor of 4. So different functions, so they are multiplied with different coefficients. So if you shift these functions, multiply with these coefficients, compress these wavelets, multiply with some coefficients, so their linear combination can give you this function. This is what is wavelet transform. Okay, so you can decompose this function using the scaling and the wavelet functions only. Okay, and again we've seen that the scaling and the wavelet function, they must be orthogonal, because if they are orthogonal, then there is Parseval's relation which says that the energy of the signal is basically given by the sum of these coefficients plus sum of djk. So it is just like in the Fourier series, okay, that the energy of the signal is basically given by the sum of the modulus of the Fourier series coefficients. Okay, it is this property which basically what defines actually what dwt is. Okay, it means the energy of this signal is basically distributed among these different coefficients. So those coefficients which have very low value or they are almost zero, so they contain very little information about this signal. Okay, so you can simply discard those coefficients. This is how signals are compressed, or the images are compressed. Okay, so next we will take one more example on this multi-resolution analysis, and we will try to elaborate in a much more clear that how you decompose a function in terms of wavelets only.